Hello friends, so welcome to this new module of this subject, that is of quantum physics. So this is the most important module of this subject. So first, let us understand what is quantum physics and the origin of the quantum theory. So as you all know that classical mechanics that we have all studied in our earlier classes have many parts such as Newton's laws of motion, gravitational law of attraction between two bodies, Lorentz force equation related to the force on a moving charged particle, and Coulomb's law of attraction or repulsion between two electrically charged bodies, etc. So it has been observed that classical mechanics can explain successfully the motion of the celestial bodies or other earthly observable objects. But when the classical concepts were applied to the particles of atomic dimensions like electrons, protons, neutrons, nucleus, etc., they failed to explain their motion. So, classical mechanics is only applicable for bigger objects, not for the smaller objects of the size of the nucleus or neutrons. So, the failure of classical mechanics to explain the energy distribution of black body radiation put forward Max Planck, the we known as the father of quantum physics, to propose the quantum hypothesis or the hypothesis for the origin of quantum physics. So this is how the quantum physics originated, and hence quantum physics refers to the physics of small particle, because quantum or quanta refers to a single part of the energy or particle. So, as we have known that classical theory does not hold good in the region of atomic dimensions, that is, for nucleus, Planck particles, etc. So, radiation of energy is usually characterized by its wave-like nature. But many experimental observations, such as the Blackbody radiation, photoelectric effect, Compton effect, pair production, etc., cannot be explained properly only by considering the wave nature of radiation. So these phenomena, along with any natural phenomena from elementary particle level to cosmological level, can be properly explained on the basis of particle aspect of radiation, that is, the quantum theory of radiation. So in that case, the waves of electromagnetic radiation behave like particles of definite momentum and energy. So this is how we can see or say that light have wave duality, wave particle duality. That is, light exists in both wave and particle nature. So now let us further move to the important topics of this chapter after all these definitions. That is the black body radiation. So first we have to know that what is black body. As we all know that any heated body emits electromagnetic radiation. So if the temperature of the body is increased, the wavelength of the emitted radiation decreases. So if the temperature of the body is increased, then the wavelength will decrease. Similarly, a heated body can also absorb radiation incident on it. So how we have to define some terms for it, for the black body. Now we will be defining what is known as emissive power, that is denoted by E lambda. So what is emissive power? Let me write the definition briefly for you. So this is basically the definition of emissive power. So what is emissive power? The emissive power of a body at a certain temperature T for a certain wavelength lambda is said to be its energy radiated normally in vacuum from its surface per unit area, per unit second, per unit range of wavelength. So this is the definition for emissive power. Now let us try to know or define another brief definition, that is about absorptive power. So here I have written the definition for absorptive power for you all. Let us read it. The ratio of amount of heat absorbed by the body, that is denoted as Q dash, to the total amount of heat Q falling on it is known as absorptive power. Now let us study some laws. The first one will be the Kirchhoff's law of heat radiation. So this is the definition for Kirchhoff's law of heat radiation. That is ratio of emissive power, that is the E lambda, this one emissive power of a body to its absorptive power, that is A lambda, this one, for radiation of a given wavelength at a particular temperature is always constant. So we can write that E lambda by A lambda, that is emissive power by absorptive power, is always a constant that we can denote as K. So this is the Kirchhoff's law of heat radiation. So after defining emissive power, absorptive power and Kirchhoff's law, so what we have concluded that in case of a black body, in case of a black body, the black body radiations absorptive power, that is A lambda, is equal to 1. So emissive power, that is E lambda, is equal to constant, let it be K1. So this is the condition for a body to become black body. So it emits constantly and the absorptivity is 1, that is it absorbs all the radiations that fall on it. So friends, if you want to construct a black body, let me show you how. So first let me tell you the final definition of a black body. So the substance or a body which can absorb all the heat radiations of all wavelengths incident on it and does not transmit or reflect at all is known as a perfectly black body. So a perfectly black body is an ideal concept. For example, platinum black, lamp black, etc. can be applied to make a body and reach the body up to the level of a perfectly black body. For experimental purposes, a black body is made up by a hollow spherical copper enclosure with a small hole, that is small orifice, in its surface. The inner surface of the sphere is coated with lamp black. When any radiations enter the spherical enclosure through this hole, it suffers multiple reflections at the inner surface until it is totally absorbed. In this way, the body acts as a black body absorber. So let me show you a small schematic diagram. You consider this as a spherical chamber with a very small orifice in it. So the inner surface is coated with lamp black to absorb the incident radiations. Fine. So light enters, and here is a deflector, you can say a curved plate, here it is. Light enters straight away through here, and after reflecting here from here, it suffers multiple reflection, and thus it is finally or totally absorbed inside the spherical chamber, or the hand hence, since it absorbed all the radiations, it acts as a black body for our experimental setup. So what are the characteristics of black body radiation? Let me explain it to you. Number one is the energy density. The energy density, that is energy radiated per unit area per second, does not depend upon the nature or shape of the walls of the enclosure. So it depends only upon the temperature of the enclosure. That is, energy is only dependent on the temperature. All the bodies placed inside the enclosure also emit black body radiations. That is, inside a black body, all the bodies must be considered as a black body too. The radiations are homogeneous in nature. So another point is that radiations are homogeneous in nature. And last but not the least, the radiations are isotropic in nature. So now we'll move on to the important parts of the chapter, that is different kinds of formula. So the first formula we will be discussing is Wien's radiation formula. So in order to explain the observed spectral distribution, Wien first showed that the energy density of radiation of wavelength lambda and lambda plus d lambda from a cavity, that is we are considering as a black body of a temperature T, can be showed by E lambda d lambda equal to A by lambda to the power 5 into e to the power minus b by lambda t d lambda, where a or b are two constants. Let this equation be equation 1. What are the limitations of this formula? Means radiation formula, that is this formula, explains only the experimental results and good enough. Now we'll go to the second law, that is Wien's displacement law. So this was the first law we've discussed, and now we'll be discussing Wien's displacement law. So what is about Wien's displacement law? It states that the maximum energy density or intensity of radiation emitted from a black body is displaced towards the shorter wavelengths for the rise of temperature T of the black body. That is, we can say lambda max is proportional to 1 by T, or lambda max T is equal to K, that is a constant. Now another important formula, that is the Rayleigh-Jeans law. So Rayleigh and Jeans applied the classical law of equipartition of energy to this electromagnetic blackbody radiation. And what they found? They found that the energy density of radiation of wavelength range lambda and lambda plus d lambda from a black body of temperature T is equal to E lambda d lambda, that is equal to 8 pi k T by lambda to the power 4 into d lambda. So let this be equation number 2 and let this be equation number 3. This was all about Rayleigh-Jeans law. So it states that the energy density E lambda of a black body is proportional, that is we can say that E lambda is proportional to 1 by lambda to the power 4. So this is the conclusion for Rayleigh-Jeans law. Now we'll move on to the next law, that is the fourth law, that is Stephen-Boltzmann law. So this law states that the total energy, that is we can consider as E dash, emitted per unit area per unit second from a perfectly black body is proportional to the fourth power of its absolute temperature. So we can write that E dash is equal to sigma T to the power 4, where sigma is the Stephen's constant. The value of sigma is equal to 5.672 into 10 to the power minus 5, that is in the unit of arc centimeter square seconds per second per Kelvin to the power 4. So if a perfectly black body at temperature T Kelvin is completely surrounded by an enclosure T naught Kelvin, that is T greater than T naught, the amount of radiant energy per unit area per second will be given by E dash equal to sigma T to the power 4 minus T naught to the power 4. This was all about Stephen-Boltzmann law. So this was the explanation, definition and expressions for 4 of the laws. Now in the next video we'll be continuing with Planck's hypothesis and radiation law, and we will derive all these laws from the final Planck's law. Thank you for watching this video.